Overmolding plastic onto a metal or plastic insert can cause the insert to deform, which will not only affect the mechanical properties of the part, but in some extreme cases can affect the functionality of the part in its desired application. Simulation can be used to predict this phenomenon called core shift to understand the impact of different molding properties on the final molded part. I'm Alex Baker, and welcome to another advanced module breakdown. The core shift module involves having a part and a part insert. The insert is what will be in the mold before the molding begins, and then the part will be what is molded on top of that, the desired final plastic part geometry. I've imported both of those models here, and so we can attribute these two objects as part and part insert respectively. I'll double click on the part, assign it as a part, double click on the insert, assign it as an insert. In order to simulate the deformation of the insert, I'll need a place for the material to be injected from. So I'll place a gate on the midpoint of this feature line here. And if I turn the model transparent, we'll be able to maybe understand fundamentally how the plastic is going to flow through the geometry. It's going to flow out of this gate, and then it's going to flow downwards, and then it's going to flow outwards to the left and right. As it flows downwards, we might be able to anticipate that it's going to deflect the insert down here on the bottom, and also the insert up here on the top. We always recommend to have a matching mesh between the part and the part insert so that we can get a good nodal transfer of data across the boundary between the two. This is very important for mechanical information. For thermal information, it's not as. We always recommend to have a matching mesh between the part and the part insert so that we can get a good nodal transfer of data across the boundary between the two. This is very important for mechanical information. For thermal information, it's not as necessary, but when we're studying core shift, we always recommend to have some sort of matching mesh. Check the box that says allow non-matching faces. This box will be checked automatically, allowing you to bypass the constraint of matching mesh. Whenever I'm doing the seating for the part, allowing you to bypass the constraint of matching mesh, but we're going to turn this off so that the mesher automatically matches these two components together. I'll go to mesh, we'll seed the part. Whenever I'm doing the seating for the part, I'll always include the part insert with it so that these two receive the same node seating. That's going to make things easier when the mesher goes to match these two components together. All right, I'll select both of these components, press the green check mark. All right, we'll see what the default seating is. Looks a little bit large if I use the Goldilocks approach from one of my other videos. And zoom in the part so that fills up the whole screen. And I want about 2 to 3 nodes width of space. We can see that there's quite a bit of space here. So I'm going to drop it down to, let's say 0.5 as a starting point. Actually, that looks pretty close. Maybe I'll go just a little bit lower. Okay, because these geometries are a little bit more simplistic, I can afford a little bit of a tighter node seating. So I'll press the green check mark. Right. When I go to generate, now I can generate. When I go to generate, because we have the allow non-matching mesh turned off, we can see that there's an additional component to the meshing hierarchy here that is called match contact faces. So what it's going to do is it's going to create the service mesh for the part and the part insert. Then it's going to match those two, reconstructing the boundary between the two. And then it'll create the solid mesh of each of these components, the part followed by the part insert, followed by the runner. Let's start off by just looking at the matching mesh, and then we can generate the solid mesh afterwards. All right, so we can see it automatically goes through and matches the contact faces. So what that's doing is it's actually going through and nodally combining these two components together. So if I were to look at the nodal structure for the part insert, the inside geometry of the part, if I turn off the part insert, we'll have an exact one-to-one matching mesh to the part insert. That's done automatically, assuming that the part insert is cut into the part. Make sure that the part is booleaned with the part insert, meaning that there's a cutout in the part with the part insert. That part is not done automatically. You'll have to do that beforehand. You can either use the tool and the subtract function, or you can do so in your CAD system. But as long as that cutout is created in the part, then the interaction between the part and the part insert is going to be identified. and then the mesh is going to be able to be meshed between the two. Now let's look at the meshing parameters for the solid mesh. So if I go into the mesh tab and then parameter, for the part, as always, we will recommend a 5-layer BLM with a 3.0 offset ratio. For the part insert here, the part insert we always recommend to be pure tetra. This is for two reasons. First of all, we're not flowing any material through the part insert, so we're not studying any flow properties. And also tetrahedral elements are really good at large scale deformation. When we're going into core shift, it's very possible that this insert deflects quite a bit. And so having a more flexible element array, like a tetrahedral mesh, will really help with the stability of the calculation. For the runner, as always, we'll just use the default 4 inner 5 outer layer template. Checkmark, generate, and then we'll generate the whole thing. Right, so this is creating that 5-layer BLM in the part. You see it very quickly created the tetrahedral mesh in the part insert, and then it goes through and does the runner. Now, very importantly, when it goes to remesh the part surface with the runner, the internal nodal array is going to change, but only on the top surface. So if I go through and chisel this, I can use the chisel command to remove a portion of my mesh so that I can see what that meshing structure looks like. So while there's a new refinement on the boundary between the runner and the part, that does not follow all the way through to the insert. The insert boundary will be unaffected. This is actually done by another meshing parameter. If I go once again up to preferences, mesh, solid, there is a checkbox down here that says keep matched faces during gate rebuild. When it goes to rebuild the mesh around the gate, that will not impact the nodal structure to the part insert. If it would cause a non-matching mesh to occur between the part and part insert, the mesher will fail, telling you that the rebuild cannot be completed. All right, so now that we have finished our mesh, we can final check. Now in the material selection, we're going to select the part material. The EM1 is the plastic material that we're injecting through our melt inlet. All right, so I'll select my plastic material, go to the material wizard. All right, so I can select my plastic material, and I can select my insert material. Like I said, this can be a metal material or a plastic material, but in this case, we're just going to use a metal insert. Beryllium copper is a very good material for heat transfer, but is not actually a good material for overmolding because of its lack of rigidity. But it makes a good example in this case. All right, there's nothing specific in the process that needs to be pointed out, so I'm just going to use a default process here. The analysis type that I'm going to use, actually you can see the core shift in the filling analysis, and in the computation parameters, there's a few things that I want to note. When you include a part insert into your analysis, you'll get a new tab in the computation parameters called MCM, MCM standing for multi-component molding. There's two things that you can do here. You can either link this with a previous shot. This would be to simulate a two-shot molding analysis. In this case, though, since we're trying to simulate core shift, we're able to go into the core shift calculation. I'll check this. There's two types of core shifts that we can run. There's a one-way core shift and a two-way core shift. In parentheses, it says FSI here, which stands for fluid structure interaction. And that's exactly what the two-way analysis is it's an interaction between the fluid, in this case the plastic, and the structure, in this case the insert. A one-way analysis allows us to simulate the impact of the pressure exerted by the plastic onto the insert, and then that pressure will deform the insert in some way. But there's no communication between the deflection of the insert and the plastic itself. Actually, in extreme cases, and we'll actually see that in this case, the deflection of this insert, if it deflects downwards, can create a very thin material structure here. And so it might be difficult for the material to actually get underneath this insert as it begins to deflect. This effect would not be able to be taken into account with a one-way core shift. That's where a two-way core shift would come into play. A two-way core shift allows us to consider a two-way interaction between the insert deflection and the flow progression. As the flow applies pressure on the insert deflects, and as the insert deflects, it applies a restriction for the material to flow around it. This communication can cause the simulation to be quite long, but the added accuracy that you get from the two-way core shift is very useful. A one-way analysis is really good at getting a trend-wise idea as to which way the insert is going to deflect. But because there's no check from the insert deflection onto the flow progression, the magnitude of the one-way core shift is typically quite a bit larger than what you would get in a two-way type of analysis. So you can run a one-way analysis as a preliminary simulation that should run in a reasonable amount of time. And then once you're satisfied with that, you can run a two-way analysis to get a more accurate magnitude of deflection. I'm going to show the difference between a one-way core shift and a two-way core shift on this example here. But before I show those results, we have one more thing that we need to apply, and that is the boundary condition. In order for the insert to deflect, there needs to be some area of the insert that is held stationary. This is what we call as a core shift boundary condition. And a core shift boundary condition will actually be applied automatically if I go to run the analysis. So if I choose to activate the core shift calculation and I hit run, it's going to create a displacement boundary condition saying that all of the nodes that are not inside of the part are held stationary. You'll want to confirm this as the simulation is running, and if it's not correct, then you can just go in and cancel the analysis. This boundary condition will appear over in the model tree. I'll delete this, and I can apply my own boundary condition manually under the Boundary Conditions tab. Under here, I'm going to apply what's called a fixed constraint. You can also apply a displacement constraint. Both of these end up being the same thing for core shift. All right, we can see when I use the fixed constraint, it automatically comes up with the core shift. If you choose auto, then it will just select all of the nodes that are outside of the boundary of the part. But if you select manually, then you can select some group of elements. Or if you select, for example, one element, it'll propagate automatically with some sort of propagation criteria given by this little gear. You can also specify which direction this insert is fixed. So if, for example, the insert is just held at one end, and maybe it's able to deflect up and down, but it's not able to deflect in the x-axis, then maybe I can just say that it's fixed in the x-axis. In this case, this insert was loaded into the mold and was clamped onto, so it would be an XYZ fixed constraint. I press OK. I can confirm that that has been applied properly. If I go over to the Home tab, Computation, if I go into the MCM tab, I'll now see that the core shift boundary condition is checked. And when I hit run, the analysis will launch automatically, and it will not create another constraint on top of this because it already identifies that a constraint has been created. I've already run the one-way and two-way core shift analysis, so let's see what the results of this looks like. For a one-way core shift, we can look at the melt front time and watch the progression through the part geometry. We can do this just as normal, result, and then we can play the animation. And the material will flow through the geometry, but you'll notice that the insert doesn't really deflect at all. And that's because we've run a one-way analysis. When we run a two-way analysis, the insert will actually deflect in the melt front animation, which is kind of cool. But this isn't what we're after necessarily. We're after the insert deflection. And so when you run a core shift analysis, there is a new result category called core shift at the bottom of your result list. I go into core shift, and then I see the total displacement, and this tells me how far the insert has deflected based on the plastic pressure onto the insert. Remember, this is a one-way interaction, so there is no check from the insert onto the flow progression. The only thing that's shown here is the impact of the pressure applied by the plastic onto the insert itself. Now, this is a deformable result, so while this just shows a color distribution showing us the displacement, like the warpage results, we can go up to deformation and see the actual displacement of this insert. Now, because this is a one-way interaction, remember that there's only the pressure of the plastic onto the insert, And so there's no boundary preventing this insert from deflecting. And so you can see actually it deflects outside of the part boundary, which is obviously unrealistic. In addition to the total displacement, you can also see the pressure on the part insert. And so this pressure is translated into a stress. That stress is where the deflection is derived from. All right, so let's check out a two-way analysis and see what the differences are between the one-way and two-way outputs. With a one-way analysis, remember we could only see the progression of flow with a stationary insert. But actually, if I go into my melt front time under the two-way analysis and play the animation, now I can actually see the deflection of the insert with the progression of flow. And that's because there's a two-way interaction where the pressure of the plastic is causing the insert to deflect, but then the deflection of the insert is also impacting the ability of the material to flow around it. This creates a constraint for the deflection and forces the deflection to be within the part boundary. If this deflection somehow goes outside of the part boundary, then you will get a divergence of the analysis, and that will show in the log file. Just like the one-way analysis, in the two-way, we also get the core shift category. When I go into total displacement, I don't even need to go into the deformation because it will automatically be deformed. We can see that the displacement is quite a bit more realistic. At least the deflection is inside the boundary of the part here. And so while the trend-wise data that we got from the one-way analysis still holds true here, the magnitude that's displayed in the two-way interaction is much more reasonable. We can also see the pressure on the insert, which the pressure on the insert should actually be similar to the one-way analysis. If I use a compare, I can put the left side as the pressure on the insert. And so we should see that the pressure is comparable on the insert between the one-way analysis and the two-way analysis. Just the two-way analysis is checked by the existence of flow around the insert. Thank you for watching this advanced module breakdown for core shift. If you have any topics that you'd like to see a video done on in the future, you can leave a comment below and make sure to like this video on your way out. You can also subscribe to the Moldex3D North America YouTube channel so you can get notified when new videos are posted that you might be interested in. Thanks for watching, and we'll see you in the next one.